16-bit register, then we are going to number from 0 to 15. We are discussing about shift micro operations in yesterday's class, and we have done with the logical shift operations and the circular shift operations. What do we achieve in logical shift operations? Why do we perform logical shift operation?
We do operations on every single bit in the register.
Okay, every single bit, and using a logical shift operations, we will be inserting a 0 in the least significant bit or in the most significant bit of the register. Okay, the data content in the register will be changed in the least significant bit or in the most significant bit. Whereas circular shift operations, we are not going to add any new bit or we are not going to delete any bit from the data content of the register. And in today's class, we will be seeing the arithmetic shift operations and the hardware implementation of shift micro operations. Say arithmetic shift, let us take an example of a register R whose bit positions are numbered from R0 to Rn-1. This is a register R which stores n bits of information. Stores n bits of information and it is numbered as R0, R1, so on up to Rn-1. Okay, or it can be 0 to n-1. The bit positions are given as 0 to r-1. So if we want to perform arithmetic shift right represented by ASHR, arithmetic shift right, if you want to perform arithmetic shift right, this sign bit, arithmetic shift operations are to perform shift left or shift right for a signed number. So the most significant bit of a binary number represents this sign. And if it is 1, it means that the number is negative number. And if it is 0, it means that the number is positive number. Okay, this we discussed earlier in unit 1. Okay, signed integers using a binary number are represented by seeing the most significant bit. You can say whether it is a positive number or a negative number. For a positive number, the most significant bit will be 1, and for a negative number, the most significant bit will be 1, and for a positive number, the most significant bit will be 0. Okay, the most significant bit signifies whether a given number is a positive number or a negative number. So here r-1 represents the sign of a number. R-1 represents the sign of a number. So when we are performing arithmetic shift right, this sign bit remains unchanged. That means it will be Rn-1 only. It will be Rn-1. Then we will be moving the other bits by right position, 1 bit right. Okay, the sign bit remains unchanged, whereas we will be performing the same shift right operation whatever we do, like a logical shift right operation. If I want to perform the logical shift operation, what can I do? Logical shift operation for a number 1101. Tell me the binary digits that you get after performing logical shift. If you perform a logical shift, what will be the number that you are going to get? Logical shift of 1101. What will be the answer for logical shift left of 1101? And what will be the equivalent logical shift right of 1101? Yes, plus after performing logical shift right, what will be the value of 1101?
Ma'am, logical shift of left is 1010.
Logical shift left is
1010.
hmm, see I have given 1101. So if you want to perform logical shift left, you will be moving one bit left, that is 011, and you will be inserting a 0 at the most significant bit. This least significant bit will be discarded. This is the logical shift left. Okay. And if I want to perform logical shift right, I'll be moving one bit right. So it will become 110 and a 0 will be inserted here. I repeat, so the given number is 1101. Okay. 1101. If I want to move left, that means I'll be moving one bit left. 101, 101, and a 0 will be inserted here. Okay. 1. I'm getting confused by it. Logical shift left, we will be just discarding this bit. This will be same and a 0 will be inserted here. We are moving left one position.
Ma'am, in logical shift left, and we discard the most significant bit, na ma'am.
Yeah, we discard the most significant bit. I'm getting.
Leftmost one will be discarded.
Yeah, in the logical shift right, the least significant bit will be discarded, and in the logical shift left, the most significant bit will be discarded. So now it will be the most significant bit will be discarded. It will be 101, and a 0 will be inserted 101, and a 0 will be inserted, right? It will be 1010 after logical shift left. And if I want to perform logical shift right for the same number, then I will be discarding the least significant bit and a 0 will be inserted in the most significant bit. It will be 0110. I repeat, in logical shift left operation, you will be moving the bit position in the initial register by one position left. You will be moving left, one bit left side. So you will be discarding the most significant bit and a serial input 0 will be inserted at the least significant bit position. Whereas in logical shift right operation, you will be moving each bit in the given register to the right position by one bit, and the least significant bit, this least significant bit will be discarded, and you will be inserting a 0 at the most significant bit position. This is a logical shift left and logical shift right. Whereas arithmetic shift, circular shift left and circular shift right, you will be not inserting any new data. For example, if you have the same number 1101, so after shift left operation, it will be 101, and whatever the bit you are discarding, that will be inserted at the least significant position. This we call it a circular shift left. And for the same number, if you are performing circular shift right, initially we will be moving each bit to the right by one position, so it becomes 110, and instead of discarding this bit will be inserted as the least significant bit, and this will be the number after performing circular shift right. Now we'll be going through the arithmetic shift right. If it is arithmetic shift right, the sign bit, that is the most significant bit of a given number, remains unchanged. The most significant bit of a number remains unchanged. Since we are operating it for the signed bits, I'm taking the same number 1101. The sign bit remains unchanged. We will be writing as it is 1. And we will be performing a same logical shift operation for the remaining bits. So it will be now 1110. Most significant bit in a given number is written as it is, as it signifies the sign of a number. And the remaining bits of a given number are moved to the right position by 1 bit. That is arithmetic shift right. Okay, arithmetic shift right. The most significant bit is directly shifted without any modification. The most significant bit is shifted directly, that is the r minus 1 bit of a given register is shifted as it is. There is no change in it. And for the next bits to form the arithmetic shift right, you are going to shift 1 bit right from r minus 1 digits. You are going to perform the same logical shift right operation whatever we have done for the remaining bits to get the remaining bits, whereas the most significant bit remains unchanged. This is arithmetic shift right. As we are performing arithmetic shift right, there is no problem with the sign of a number. We are directly shifting it, and the result whatever you are getting will be with the same sign that you have in a given number. Will have the same sign. But when we perform arithmetic shift left, see, I have arithmetic shift left. From R0 to R minus 1 we have, R minus 2 we have. So in order to perform arithmetic shift left, what we do, we discard the r minus 1 bit. We discard the r minus 1 bit, and it is shifted from r0 to rn minus 2. R0 to rn minus 2 will be the result number for the arithmetic shift right, shift left also. Whatever we have done, the same thing we are going to do in arithmetic shift left also. It inserts a 0 in the R0 position. It inserts a 0 in the R0 position, and it will shift left 1 position to perform arithmetic shift left operation. And the initial bit whatever we have, R minus 1 is lost. R minus 1 is lost, and it is replaced by the bit from R minus 2. R minus 1 is lost, and it is replaced with R minus 2. For example, we have 1, 1, 0, 1, 1, 0, 1. If we have a number like this, then the result will be 1, 0, 0, 1, 1, 0, 1. Now this will be the number after performing arithmetic shift left. This one will be lost. This one will be lost. But here the problem is arithmetic shift left or arithmetic shift right is performed for the signed integers. As we have the same sign, that is 1 and 1 in r minus 1 and r minus 2, there is no problem, because the result is also giving a negative number and the original number is also a negative number. Since the most significant bit of a given number and the result is 1, the most significant bit in the result and the most significant bit in the given number is 1. So there is no sign reversal for this number. Since r minus 1 and r minus 2 are having the same sign, r minus 1 and r minus 2 are having the same sign. After arithmetic shift left operation, r minus 1 is discarded. R minus 1 is discarded, and the result is a 0 through R0 to R minus 2. 0 through R0 to R minus 2. That means we will be inserting a new 0 at the least significant position, and whatever the number you have from R0 to R minus 2 will be there as it is. Since R minus 1 and R minus 2 are having the same sign, the result is not doing any sign reversal. But what if a given number is 1 0 1 0 1 0 1? Let us consider this is the given number. So the result will be 0 1 0 1 0 1 0, and this bit will be discarded. This is the R minus 1 bit. It will be discarded after arithmetic shift left operation. The given number is a negative number because the most significant bit is 1 here. But the result you are getting as a positive number. That means by this arithmetic shift left or shift right, you are doing a sign reversal. There is a sign reversal in this case. So there might be a overflow in this condition. There may be a overflow of information in this condition. So it can be seen whether there is a overflow or not. It can be detected. Arithmetic shift left overflow can be detected by using the formula Vs is in order to detect the overflow and store the result. We will be performing Rn minus 1 exclusive Rn minus 2. Here it is 1 exclusive 0. If the result is 1, then it means there is a overflow and a sign reversal occurs after the shift operation, and whatever the overflow bit you got, that must be stored in this flip-flop Vs. If there is a sign reversal and if overflow is expected, that must be stored in this register Vs. Okay. And in the previous example, see Rn minus 1 and Rn minus 2 are having the same sign 1 and 1. Vs equals to Rn minus 1 exclusive Rn minus 2. 1 exclusive 1 equals to 0. That means there is no overflow detected and Vs will not store any information in this case. But if there is an overflow expected, that can be detected by performing the XOR operation on R minus 2 and R minus 1 bits. If there is an overflow, that must be detected and it must be transferred into the overflow flip-flop Vs. It must be detected and it must be transferred into the overflow flip-flop, and that occurs in the same clock cycle. And it shifts whatever the information you have in Vs to the intended location in the register. So this is about arithmetic shift left and arithmetic shift right. Is it clear, or you want me to repeat all the three types of shift operations once again?
Ma'am, repeat once again.
Yeah. See, we have three types of shift operations. One is logical, the second one is the circular, and the third one is the arithmetic shift operations. First one is the logical. The second one is the circular shift left and shift right operation. And the third one is the arithmetic shift left and arithmetic shift right operation. See, in logical shift operations includes a serial 0 in the most significant bit or in the least significant bit of a given number. Whereas the circular shift operations will not add, no change, will not add any new bits or will not add, delete any, will not discard any bits. Whereas arithmetic shift operations can be performed whenever you want to move the bits left or right of a signed numbers. This is applied for the signed numbers. Okay. Shift left is nothing but you are shifting each position in a given register, each position data of a given register to the left by one position. Shift right is nothing but starting from the most significant bit, you will be shifting right by one bit position. Okay, logic. So let us take an example. This is the given register in to perform all the operations. This is the given data which in which you have to perform all the three operations: logical shift, circular shift, and arithmetic shift, both the shift left and shift right. So logical shift left is represented by SHL, shift left, whatever the register. If we consider this as a register R, then it can be given as a shift left register R. Shift left register R. So shift left means what? Starting from the least significant bit will be inserted with 0 and the bit positions are moved left by one position. Are moved left by one position. Will be inserting a serial 0 in the least significant bit and will be moving each bit in the given register by left by one position, and the most significant bit will be discarded. This is the logical shift left operation representing by SHL. This is the name of the register R. And if you want to perform the logical shift right, it is represented by SHR, shift right operation on register R. It can be A, it can be B, it can be C, it can be R, whatever the register you are using. Shift right register R. If you want to perform the uh, shift right operation, then the most significant bit will be added 0. The 0 will be added in the most significant bit of a given register, and you will be moving one bit right for the given number, one bit right. And whatever the data you have in the least significant bit will be discarded. Least significant bit will be discarded. Okay. In shift left operation, most significant bit will be discarded. In shift right operation, the least significant bit will be discarded. Okay. Here 0 will be inserted in the least significant operation, least significant bit while performing shift left operation. 0 will be inserted in the most significant bit while performing shift right operation. And if it is a circular shift left or circular shift right, instead of adding a 0 in the most significant bit or in the least significant bit, we will be replacing with the bit we are discarding in the logical shift left or logical shift right. Let us consider this is the register R, and if you want to perform circular shift left of register R, circular shift left of register R, so you will be moving the data one bit left. See, one bit left, 101, and this one, instead of discarding, this one will be inserted here. Okay, now 1011 is the data that you get after performing circular shift left on register R. And if you perform circular shift right on register R, circular shift right on register R. Shift right operation, usually we will be discarding the least significant bit, right? So it will be 1, 1, 0. Instead of discarding this least significant bit, it will be added here and it will be 1. Instead of adding a 0 in the least significant position for after performing a shift right operation, we will be uh, replacing it with the bit that we are discarding in a logical shift left or logical shift right. Okay, this is a circular shift left and circular shift right. And arithmetic shift right, 1, 1, 0, 1. While performing arithmetic shift right, ASHR of register R, arithmetic shift right, the most significant bit will not have any change. It will be dropped directly. It will be 1. And the shift right operation is performed to the next bits, starting from the most significant bit. So it will be 110. This is most significant bit is directly shifted, and the same logical shift right operation is performed as we do. And for arithmetic shift left operation, arithmetic shift left operation, a 0 will be inserted in the least significant position and the same logical shift left operation will be performed. 101. Okay, 101. And check if r minus 1 and r minus 2 are having the same sign or not in the given data. If they are having the same sign, then there will be no overflow. Arithmetic shift left operation will not cause any overflow, and uh, it can be it will be the final result. That means there will be no sign reversal when we perform arithmetic shift left operation. But if r minus 1 and r minus 2 are not having the same bit values, 1 and 1 or 0 and 0, then we can detect a overflow while performing arithmetic shift left operation, and that must be transferred into a register vs. The overflow, whatever you get, that must be transferred into a overflow flip-flop. This is arithmetic shift left operation. These are the three shift micro operations that can be performed. Now let us see the hardware implementation of uh, the shift micro operations using a 4-bit combinational shifter or a circuit. 4-bit combinational shifter. So how? See, in order to see the working of this circuit, you go through the truth table given here. The truth table given here. This logical diagram or this combinational circuit is used to perform the shift right operation and to perform the shift left operation. How? See, for this I'm using a I want to operate on 4-bit register that which is having 4 bits of information. I'm calling it as A0, A1, A2, and A3. Okay, these are the 4 bits of information on which I want to perform shift left or shift right. I have two choice only, whether to perform shift left or to perform shift right. So I'm using a 2 by 1 multiplexer. Okay, I'm using a 2 by 1 multiplexer. So how many data selection lines I have for a 2 by 1 multiplexer? Data select lines, possible select lines for a 2 by 1 multiplexer are
1.
1. So I'm considering it as yes. It can be a 0 or it can be a 1. Okay, when it is 0, I'll get different output from the multiplexer. When this select line is 1, I'm expecting different output from multiplexer. So I'm choosing to perform shift right operation when s equals to 0 and shift left operation when s equals to 1. Okay. Shift right operation when s equals to 0 and shift left operation when s equals to 1. Okay. When s equals to 0, I want to perform right. When s equals to 1, I want to perform left. Since I have 4 bits of information here, I'm using 4 multiplexers of 2 by 1. 4 2 by 1 multiplexers I'm using. Two by one, 2 by 1, 2 by 1, and 2 by 1 multiplexers. Okay. And selection lines, only one selection line. I'm representing it with S, connecting to all the multiplexers. Okay, this is S. Yes. See, S can be 0 or S can be 1. 0, I want to perform right. And when it is 1, I want to perform left operation. So let us first go through the truth table. For this multiplexers, I'll get one output from each. I'm representing it as H0. I'm representing it as H1, H2, and H3. Okay. And what can be? It can 0 can be selected or 1 can be selected at each time. 0 or 1. Okay, 0 or 1 can be selected at each time. Let us see how these operations are performed. I'm writing the functional table or the truth table. S can be 0 or S can be 1. Output expected is, see, the possible outputs are H0, H1, H2, H3. Since I'm giving the parallel load here, I'll be getting the output at a time from the 4 multiplexers. Okay. So I'll be giving a serial input IR here, A0, A1, A2. Because in the write operation, the most significant bit will be inserted with a new information. And when it is 1, I want to insert A1, A2, A3, and the new information, whatever the input you are getting from IL, that I want to insert. And in this way, shift left and shift right operations can be performed. See, when I want to perform shift right operation in the most significant bit, I'm inserting the new data by giving it as a serial input IR. And I'm connecting A0 here, A1 here, and A2 here. So A0, A1, A2, I'm connecting in this way so that I'll get the output IR, A0, A1, and A2 after performing shift right operation. Whatever the output we are expecting, that we get by giving the inputs in this way. Okay, serial input is given for the first multiplexer, and the remaining bit positions whatever you have. For example, you have 1010 here. So whatever the IR, it can be a 0, it will be inserted, and A0 101 will be the output, which will be the output after the write operation, after the shift right operation. The same thing we are achieving by constructing the logical circuit in this way. 101 you got, right? This will be the data that you will be getting from the actual data after performing the shift right operation. And whatever the serial input is given, that input you are getting from the IR, which is given to the multiplexer. Okay, shift right operation is performed when we have 0. And now let us see the 1. That is how we are going to perform shift left operation. In order to perform shift left operation, this fourth multiplexer, we are going to give whatever the serial input you want to give, that input is given, and you will be getting the same at H3 position. Then A3 you are connecting to H2. That means this A3 is connected here. A3 is connected to the one data input line of this multiplexer, and A2 is connected to the H1. A2 is connected here, and A1 is connected here. A1, A2, A3. Here whatever the information you get, A1 is 1, A2 is 1, A3 is 0, and whatever the serial input you are supplying, that output you are going to get here, IL. In this way, shift left operation can be achieved for whatever the data you give for a 4-bit register. When S equals to 1, we are performing shift left operation by connecting the input registers A0, A1, A2, A3 in this manner to the data select line 1, S equals to 1. And when S equals to 0, you are connecting IR, serial input, to H0 multiplexer, A0 to H1, A1 to H2, A2 to H3, so that you will be getting the shift right operation, result of a shift right operation as the output from the multiplexer. In this way, shift micro operations can be performed by using this hardware implementation. Is it clear? Hardware implementation of shift micro operations. Yes, class. Hardware implementation of shift micro operations. Is it clear? 18, 54, 56. Yes or no? Let me know anything, class. Is it clear or not? 54.
Yes, ma'am.
Say something, right? If you have understood, say yes. Otherwise, no, so that I can repeat.
Ma'am, and you can once again repeat, ma'am.
See, in order to perform shift micro operations, I'm using 4 2x1 multiplexers. 4 2x1 multiplexers. Okay. If you want to perform a shift right operation, usually in the most significant bit, you will be adding the new data, whereas you will be moving the other bit positions to the next locations. 1, 2, 3 positions will be occupied by 0, 1, 2 positions of the previous register. Yes or not? Shift right operation. For example, you have A0, A1, A2, A3 in your register. You have 4 bits of information like this. So A0, A1, A2, A3. For example, you have a register content like this. So if you perform shift right operation, what data you will get? You will get A0 at this position, A1 at this position, A2, A2 at this position, and whatever the new data according to the type of the shift operation you are performing, the new data will be inserted in the most significant bit. So the same thing I want to perform when I'm using s equals to 0. Okay. And the same data you have A0, A0, A1, A2, and A3 are the bits that you have in a register. Got stuck. See. And to perform shift left operation, I have the data like this: A0, A1, A2, and A3. If I want to perform shift left operation, what we do? We discard this, and here it will be A. Shift left operation, it will be A3, A2, A1, and whatever the data you want to insert, it will be there at this position. That I'm calling it as IL. Any serial input here, since I'm giving it as IL, I'm writing the same in the truth table IL. IR will be inserted for shift right operation, and IL will be inserted for shift left operation. Okay. So when s equals to 0, I want to perform the shift right operation. And when shift s equals to 1, I want to perform shift left operation. For implementing that, I'm using 4 multiplexers. That is 4 2x1 multiplexers. Okay. Shift right can be also called shift down. And shift left can be also called up operation. Okay. So I have connected this information, whatever I have in the register, in such a way to each the multiplexer to get the output of shift right when s equals to 0. And I have given the path from the data in the register to the multiplexers in such a way in order to perform shift left operation when s equals to 1. How? See, for A0, when s equals to 0, this IR is connected to the 0th line, and A naught is connected to the 0th line of the second multiplexer. A1 is connected to the 0th line of third multiplexer. A3 is connected to the 0th line. The 0th line of fourth multiplexer is connected to A2. So whatever the output you get here is IR, A naught, A1 and A2. That means you are doing the same thing whatever we do in the shift right operation, right? You are moving down A naught at H1, A1 at H2, A2 at H3. You are moving one bit down and you are adding the serial input whatever you get at H naught position. This is same what we do in a shift right operation. And when s equals to 1, when s equals to 1, you are moving one bit up. That means serial input you are giving for the fourth multiplexer and the output you get is IL. And here the data select line 1 is connected to A3. At H2 you are getting A3 and at H1 you are getting A2. At H0, you are getting A1. See, A1 is connected to H0. So you are moving one bit up while performing shift left operation. So whatever the new data you want to insert, it will be inserted at the lowest bit. This is how we perform shift left operation. You are moving one bit up. Okay. It will be moved to the most significant side by one bit left, that we are calling it as shift left operation. Shift right, you are moving one bit down. So it can be also called shift down operation. In this way, when s equals to 0, shift right operation is performed. When s equals to 1, shift left operation will be performed. Okay, this is about shift micro operations hardware implementation. So we have seen what a register transfer language is, what are arithmetic micro operations, logic micro operations, and shift micro operations. And also we have gone through a arithmetic circuit, that is a 4-bit arithmetic circuit which performs all the arithmetic micro operations using that hardware implementation. Using one circuit, we have discussed how to perform all the arithmetic operations in it. And we have discussed the logical micro operations implementation using a 4 by 1 multiplexer. 4 by 1 multiplexer which will perform AND or complement and XOR operations. Now we have discussed the shift micro operations which can be performed using combinational shifter. So there is a hardware implementation, there is a hardware circuit in which we perform all the arithmetic, logic, and shift operations using a single circuit. Arithmetic, logic, shift micro operations can be achieved in a single circuit, in a common circuit, that we call it as arithmetic logic shift unit. Okay, here whatever you're seeing on the screen is to perform all the arithmetic, logic, and shift operations using a single circuit for 4 bits of information. Okay, 4 bits of information or any bits of information can be performed. We are discussing about a single stage, single input. AI and BI is given. Okay, one stage of a arithmetic operation. I is the bit position. AI and BI, and for that input how different operations can be performed using this single circuit. Okay, here the arithmetic circuit implies whatever the 4-bit arithmetic circuit we have gone through. Okay, 4 by 1 multiplexers are there. Here this I'll show you. The arithmetic circuit implies this circuit, 4 by 1 multiplexers, and which each full adder will be having 3 inputs, x0, y0, and c0. And for each multiplexer, your output is obtained by one function d. D equals to a plus y plus c in. D equals to a plus y plus c in is the output that you are getting from each multiplexer in a arithmetic circuit. So in the arithmetic logical shift unit, the arithmetic circuit implies this circuit at one stage of AI and BI. I is the bit position in the register A and B, and logical unit means that logical unit in that diagram means that this circuit where for any two numbers A and B, how we are performing the logical operations using this multiplexer. Okay, 4 by 1 multiplexer. It means logical unit means that one. So now we'll be seeing how we can perform all the operations using this single circuit. Okay, this arithmetic circuit implies that 4-bit arithmetic circuit. Logic circuit implies one stage of the logical circuit at the bit positions AI and BI. So, and the final output for all the arithmetic, logic and shift operations depends upon the input that you give to this 0, 1, 2, 3. These inputs of this final multiplexer defines what operation is performed in this circuit. Okay. See the zeroth line of this multiplexer, the zeroth line of this multiplexer is connected. The zeroth line of this multiplexer is connected to the output of arithmetic circuit. Okay, output of arithmetic circuit DI. That means we have seen the 8 operations can be performed using the arithmetic circuit. That is the increment operation, decrement operation, carry with addition, carry with addition with carry, addition without carry, subtraction with borrow, subtraction without borrow, transfer operation. That means whatever the content you have in A is transferred using this output D. So the output of the arithmetic circuit is connected to the 0th selection line of this multiplexer, and so the same is given. See, the same is given in the table when and this selection lines the selection lines for this multiplexer are S3 and S2. S3 and S2 are the selection lines for this multiplexer. For this multiplexer, S3 and S2 are the selection lines for this multiplexer, and whereas S1 and S0, S1 and S0 is for this multiplexer, and S1 and S0 the same selection lines you are using for the logical circuit also. So when S3 equals to 0, S2 equals to 0, we are performing all arithmetic operations for various selection lines of S1 and S0 in arithmetic circuit. So this S1, S0 can be 0, 0, 0, 1, 1, 0, 1, 1. For all the data input lines of S1 and S0, you are performing arithmetic operations when S3 equals to 0 and S2 equals to 0. Okay. When S2 equals to 0 and S3 equals to 0. So S3 equals to 0 and S2 equals to 0 can be seen in all these things. Still here, S3 and S2 equals to 0. That means still here all the arithmetic operations are performed. And for this arithmetic circuit, we have 3 inputs. That is S1 and S0 are the selection lines. And for each selection line, carry can be 0 or carry can be 1. So when S1, S0 equals to 0, 0 for carry 0 for carry 1. When they are 0, 1 for carry 0 for carry 1. When they are 1, 0 for carry 0 and carry 1. When they are 1, 1 for carry 0 and carry 1. Till here, whatever the operations we are seeing are the operations that we discussed in a 4-bit arithmetic circuit. Okay, by selecting the data select line as 0 of the multiplexer which is having the select lines S3 and S2, arithmetic operations will be performed. Arithmetic operations will be performed. And when the one here in for the next operation, the data select line 1 in the circuit is selected. Here 1 is selected and this 1 is connected to the output of the logical circuit. Output of the logical circuit. Again, this logical circuit is connected to the S1 and S0, which are the data select lines for this logical circuit. That means again it can have four possible combinations: 0, 0, 0, 1, 1, 0 and 1, 1. And carry is not there in this logical operations. That is why I'm writing the carry as XXXX. There is no carry for the logical micro operations. I'm writing it as XXXX. And when it is 0, 1, when it is 0, 1, see, and it is a 0, 1 common because this multiplexer one line is connected as the output of the logical circuit. For data select line 1 of S3 and S2 we are performing logical operations. So 0, 1 is common for all the logical micro operations. These are the values of S3 and S2. And S0, S1 can be 0, 0, 0, 1, 1, 0, 1, 1. Okay. So what operations are we performing? When it is 0, 0 AND operation, when it is 0, 1 OR operation, XOR operation and complement operation. This we have discussed in the logical hardware implementation. So output of logical circuit, since we are connecting to the one data input line of the multiplexer which is having the data select lines S3 and S2, we are performing all the logical operations. So now we have two other data inputs that can be given to this multiplexer, that is 1, that is this 2, this is 2. We are directly connecting to AI plus 1, AI plus 1, nothing but you are moving one position down, which is the shift right operation, and you will be getting the output after performing the shift right. Whatever you get, that output you will get. And the data select line 3 is connected to AI minus 1. That means you are performing shift left operation. So using this output, which is given as the 0th selection line, 0th input of this multiplexer, all arithmetic operations are performed. At one position, all logical operations are performed. At two position, all shift right operations. At three, all shift left operations can be performed. So when S3 is 1, 0, you are performing shift right. When it is 1, 1, you are performing shift left. So for this shift operations, there is no use of this multiplexers, whatever you are using here and here. That is why I'm denoting with X. No S1 and S2 are involved in the shift operations. That is why we are writing it as X, X and X. In this way, using this single circuit, you can perform all the arithmetic, logic and shift operations. Okay, this is the arithmetic logic shift unit. Is it clear? Arithmetic operations, logic operations and shift operations. If you have any doubt in the first subunit of unit 2, let me know so that I'll discuss. I'll revise all the arithmetic, logic and shift operations in the third class, and then I'll start the new topic. Do you want me to repeat all the operations once again, all arithmetic, logic and shift operations? Or is it clear? Do you want me to repeat all these three operations once again in the third hour?
Yes, ma'am.
Yeah, I'll do that and then I'll start the next topic, which is the instruction codes. Thank you all. Give me your attendance. Second. Roll number 1. Roll number 1, 2. Roll number 3, 4, 5. Roll number 5, 6,
Present, ma'am.
7, 8. Roll number 8. Roll number 9. Please make it fast. 10.
Present, ma'am.
11.
Present, ma'am.
12. 13. 14. 15. 16.
Present, ma'am.
17. 18. 19. 20. 21. 22.
Present, ma'am.
23. 24. 25. 26. 27. 28. 29.
Present, ma'am.
30. 31. 31. 32. 33. 34. 35. 35. 36. 36. 37. 38. 39. 40. 40. 41. 42. 43. 44. 45. 45. 46. 47. 48. 48. 49. 49. 50. Roll number 50. 51. 52. 52. 53. 53. 54. 55. 55. 56. 57. 58. 59. 60. 61. 61. 62. 61. 62. Roll number 1, 12, 29, 31, 37, 40, 43, 46, 48, 50, 51, 52, 53, 57, 61, and 62.
Ma'am, 12 present, ma'am. Mic is not working.
Ma'am, 62 is present, ma'am. I raised my
Ma'am,
hand.
29.
Ma'am, 2 is present, ma'am. I was
Yeah.
facing
Ma'am,
some issue
46
with
is
my
present,
laptop.
ma'am.
Then why didn't you respond? Okay. You
12
can leave the
present.
class.
Ma'am, 62, I raised my hand.
Ma'am, 1 is
Okay.
Ma'am, 46 present, ma'am.
Okay.
48 present, ma'am.
What were you doing when I was calling your numbers? Okay. Join for the next class, guys.